Okay, so we've been talking about kinetics, and we're going to finish that up today. This is starting at 13.5, which is temperature and rates. So we've talked about like rate constants, that those exist, and they change based on temperature, right? Because if you've got more temperature, that means more kinetic energy. And that means that you're going to have more collisions and you're going to have a faster rate. So things change. So about how are they related? Well, about every 10 degrees or so, that about like doubles the rate. Let's see if everything's going to work today. Times 2 the rate. Because it's based on a lot of other things as well. So it's not like every degree will make the rate go up faster. Kinetic energy in collisions, they're not exactly directly proportional. And that's just because they're also, like those collisions, also affected by not only kinetic energy, but like density of your substance, density. There's a lot of unsuccessful collisions. Etc. Okay, so collisions are going to be based on a lot of things, and the rate obviously is also based on a lot of things. If you graphed it, generally, this is what happens as the temperature changes, then the rate constant is going to change. So again, this is just a recap of collision theory, that it's based on two things. In order to have a successful reaction or a successful collision, you have to have the correct orientation. And that's what this picture is showing right here. Sometimes if they collide incorrectly, you're not actually going to create the products. These are ineffective collisions. They're not in the right orientation. It's not supposed to hit head on like this. That's not where they bond. So you just end up back with your products. Whereas an effective collision, essentially these have to hit in such a way that the blue one, which is the nitrogen, is going to hit one of these oxygens. And that is an effective collision. So they have to be facing the right way in order to make the right new bonds that they're supposed to be forming. So that's one important thing. The other thing is enough energy. Okay, if they don't have enough energy, they're just going to brush by each other and not bond. If they have enough energy to actually make that new bond, then they're going to get a reaction. And what is that energy called? We talked about this before. This is the activation energy. Okay, and that's going to be represented as EA, okay, energy of activation. So essentially here, I'll give you a definition for that. You should probably already know, but energy needed for successful collision. Okay, so when you have a successful collision and a successful reaction, you're going to get a nice reaction profile like this. Okay, this says reaction coordinate. Essentially, as the reaction goes on, nitrogen oxide and ozone react together. So they come together, you get the activation energy, which is enough energy to bond them and make what's called an activated complex. Now, this thing where they're bonded represents this effective collision here, not very stable, okay? Eventually, then those will fall apart and you'll end up with your products, which are NO2 and O2. Notice those are at a much lower energy, going to be much more stable. So the activated complex is the thing you see at the top of the reaction coordinate. Okay, that is the complex from collision. Complex, or I'm going to put the complex at collision. Okay, it is very unstable. Right, it's going to fall apart. This is the highest energy complex, and then it falls apart, and then you get your new products, which are going to be much more stable. Okay, so things you need to note about a reaction coordinate diagram. That's what this is referred to as. It's always going to show you the energy or the potential energy at which your reactants and your products are at. Okay, so the difference between my reactants and my products, represented by this arrow here, is the change in energy. Okay, change in energy, we know, tells us if something is going to be endothermic or exothermic. Notice this is negative because the energy went down. So this was an exothermic process. Okay. The other thing that you're going to be able to tell is the activation energy, and that's from the reactants to the activated complex. That's the activation energy. Okay, so EA is from the reactants to the peak, right, or that activated complex. And you can also tell the change in energy, which is the difference from your reactants and your products. and products. Okay, and this again will tell you if it's endothermic or exothermic. So your reaction diagram might look like this. These are kind of the two options. Notice activation energy is always positive. It always requires energy to get from my reactants to my activated complex. Okay, that one's always going to be positive. But the delta E, or the energy related to the reaction, is either going to be positive or negative, the difference between the reactants and products. And that's actually going to tell you if you are an endothermic process or an exothermic process. So if something starts at a higher energy than it ends at, that must have meant that it lost energy. Notice delta E is less than 0, it's negative. So this would have been an exothermic process. Whereas in this case, to get from my reactants, which are at a low energy, to my products, which are at a higher energy, this is a delta E is positive, which means it was an endothermic process. It ends at a higher energy than it started at. Okay, so you can actually tell that. You can tell a lot from a reaction coordinate diagram. We're going to get back to those in a little bit. Okay, so how is everything related mathematically? Can we calculate activation energy when our temperature changes? Of course we can. The actual equation, this is called the Arrhenius equation, is K equals A times E to the, and the power is negative EA over RT. Okay, this is an equation I would give you, but you should be able to use it. So what does everything stand for in this case? A is the frequency factor. Okay, this has to do with the collisions that are made, the successful collisions. This is going to be different for every reaction. Most of the time, honestly, I'm not going to give you the frequency factors, so we're going to have to use a different form of this equation, but that is what it stands for. EA is, of course, activation energy. Remember, activation energy is always going to be positive. Can't have a negative activation energy. R is the gas constant. Okay, and we're going to use it in the form 8.314 joules per mole Kelvin. Okay, that's how our units are going to end up working out. And then T is, of course, temperature. Has to be in Kelvin. And so that our units work out. All right, so this is the Arrhenius equation. And actually, I'm going to rearrange this equation algebraically into a different form. So if I were to graph, and this kind of shows the relationship, there's actually a relationship between the negative log of K and 1 over T. And this is something you'll do in lab, so please pay attention, okay? So if you are to graph 1 over temperature in Kelvin versus the natural log of K for a reaction, so essentially, you're going to find K at different temperatures. If you're going to graph this, you are going to get a nice straight line, okay? Which is great because then the slope is actually negative EA over R. Okay, so you're going to do this in class, okay, or in lab, actually. You're going to graph this and you can determine EA from there, okay? That's kind of important. So the linear equation, essentially we're linearizing this data, is the natural log, oops, sorry, I don't know why I put an I in there. The natural log of K equals negative EA times 1 over RT plus ln A. Again, I'm not going to give you A all the time. So this equation can be really helpful if you have data to graph and you can actually find the slope. However, if you only have 2 points, you can also find the slope of a line, right, with 2 points. So if you had 2 points, like 2 different Ks at 2 different temperatures, we can rearrange this equation. It's going to be the natural log of K1 over K2 equals EA over R times 1 over T2 minus 1 over T1. All right, so this equation is going to be extremely useful, especially when you're doing your homework in determining K or activation energy of something along those lines, okay? So we're definitely going to be using these equations quite a bit to determine K at different temperatures. So this is an example problem. What is the activation energy for cricket chirps given the following data? So this happened. I gave you chirps per minute and temperature. I would want you to graph natural log of K versus 1 over temperature. So I already calculated natural log, and you graph it and you get this nice straight line with this equation over here. And we know that the slope can tell us the activation energy. So if I want to find the activation energy, I know that the slope equals negative EA over R. Okay, so that's pretty easy. Negative 6622 equals negative EA over 8.314 joules per mole Kelvin. And then you're going to end up with activation energy is 5.51 times 10 to the fourth joules per mole. Okay, that's how much energy you need for each mole. Sorry, that was supposed to be a box. To overcome that hump, right, to get it to react. Okay, so you can calculate activation energy from data that way. Now, I would like you to try example number 11. So pause the video here, do your work, and then check your answers for number 11 using the equations that we just did. Okay, so I'm going to talk through these really quick. And if you're good, then you can just kind of skip ahead. So for part A, I used the 2-point equation. Again, I didn't give you that A value, so the only one you can use is the 2-point equation. Plugged everything in, solved for activation energy. I got 1.66 times 10. Well, that should be times 10 to the fifth. Sorry, I don't know what happened there. There we go. Joules per mole is going to be your unit again for activation energy. Okay, same equation for part B. I just wanted to use 700 and actually solve for K2. This one uses a little bit of algebra, so watch your natural logs there. You should end up with K2 is 0.0313 per molarity seconds. Okay, same unit as the other one. Your K's should have the same units, all right?